reactions, and specifically how to get from a written reaction to a balanced reaction. Now, we've talked about how to go from word to skeleton, like by themselves, skeleton to balanced by themselves. And now we're going to talk about putting all of those steps together to go from written to balanced. As a reminder, here are the order of completion. You should be able to start on any step and work your way to step 4. And wherever you start, you do have to do all the steps below it. So the first step is to go from written. Your second step is to go from word. So you go from written to word. Then you go from 2 to 3, which is from word to skeleton. And then you go from 3 to 4, which is from skeleton to balanced. So next, let's talk about how to read the items from a written equation to go to a word equation. Now, we know a written equation is all in words, and we know that when we're going from written to word, we have to leave the elements and chemical formulas or the compounds as words, but everything else turns into an equation format. So what do those actual words actually signify when writing an equation? So if you see the word solid, you're going to write it as parentheses, small s, and parentheses. If you see the word liquid, you're going to write it as parentheses, small l, and parentheses. And that's, I use a lowercase l for that. For gas, we're going to do parentheses, small g, and parentheses. And then for aqueous, we're going to do parentheses, AQ, and parentheses. And this is what it stands for in equation format. And please remember, for all of these items, you're going to write them after the compound, after your element or the compound. That it represents. Those are all the different states that we're going to be looking for. You might see words like reacts with, mixes with, and. There's a bunch of other ones, but these are good examples. These all mean you're going to put a plus. Those all represent a plus. You might see the words produces, decomposes, synthesize, creates, magically recombines, abracadabra. Anything that shows that these things are moving together, these all can mean arrow. And then again, there's a bunch more. Reacts with, reacts, switches places, all of those different things might mean arrow. This can be on either side of the equation. This is only specifically going to be found in the middle where the arrow would be found. Okay, next we're going to discuss how to go from a fully written equation here to a balanced equation. So the first thing I'm going to recommend is you can pull out a highlighter, you can underline. I'm going to be underlining in orange all of the words that need to be translated into your symbols. So you're going from written to word, everything is in symbols, but your elements and your compounds. So you can do this. We're going to be doing this in steps. That's why you step through it. So solid needs to be put into a symbol form, and that solid goes with the word iron. And so you can put right above it what it represents. That's S. We know and needs to be put in symbol form. That is a symbol of plus. Chlorine gas, that gas needs to be put in symbol form. That's lowercase g, and that goes right with chlorine. And if you always kind of point at what it goes with, it's going to help you to figure out how it's being written and what's actually happening. React to create. that is your arrow. That whole sentence literally just means you're going to put your arrow there. And then solid iron 3 chloride, that solid, again, is written like this, and that goes with iron 3 chloride. So we're going to write it in words now, or words. So we're going to go from written to word. So we don't represent this solid, we write iron. And then after iron, we write this S that we've outlined. And as a plus. Then chlorine gas, we write chlorine. And then you're going to go ahead and write the G after it, because you do have to represent the state of matter that it's in. React to create is our arrow. And then iron 3 chloride is a compound or an element. So we write that in words. And we go ahead and put the S after it because we still have to represent the state of matter. So this is how we've gone from written to word. Okay, now that we have the word equation, we have to go from word to balanced. Now we've talked about how if you have a polyatomic and you can see them on both sides, then you can treat them as one. Well, the cool thing about word equations is that you can physically, or for the most part, see your polyatomics. Now these aren't polyatomics, but it's good to know. So what we can do is begin to color code right here in our equation. So we're writing our skeleton equation in color-coded format. So again, I'm going to recommend you underline your word equation, the colors you're going to use for your skeleton equation. And remember, with skeleton equations, it is an unbalanced equation with just balanced compounds. So iron, we can find it right here, and we see iron over here. So I'm going to use this pretty purple color for iron. And then chlorine is right here. I'm going to use this pretty red color for chlorine. I'm going to use, remember, chlorine and chloride go together. I'm going to use this pretty red color over here for chloride. And now I'm going to go ahead. I'm going to keep a different color for my symbol so that we can see how it all ties together. So iron in and of itself is just Fe because it's a element we don't have to worry about balancing. So we can write Fe and then S and then plus, and then chlorine we're doing in that red color. Now remember, chlorine is diatomic, and just a reminder, your diatomics are your chlorine, bromine, fluorine, iodine, hydrogen, nitrogen, and oxygen. So diatomic means in gas forms, it comes in pairs. So this is Cl2. And then you put G after it. You're going to go ahead and do your arrow. And then iron 3 chloride. This is an ionic compound, so you should be using either your LCM method or your crisscross method to balance. And this is Fe. And then Cl3. And then you're going to go ahead and do the S after it. And this is your skeleton equation. Remember, I get a lot of questions. Well, I thought we don't use subscripts to balance equations, and you don't. So please remember, subscripts are for balancing compounds, and that's what you're doing in the skeleton equation. And then coefficients are used to balance equations or a balanced reaction, which you do in the balancing step. Okay, so let's balance. I'm going to be using the color-coded molecule method. If you want to use the number method or a counting method or any of the other methods we've talked about, that's totally reasonable. But for now, we're going to do the color-coded method. And remember, you always have to produce one of the molecules first to represent what's in this line. So I'm going to do one purple dot for iron down here. I'm going to do 2 dots for chlorine because there's 2 molecules in each chlorine. That's what di means, is 2. I'm going to do 1 dot for iron over here, with 3 dots for chlorine because for every 1 iron, you get 3 fluorides. Now our irons are happy, but our chlorines are not. We have 2 over here, we have 3 over here. We're gonna have to balance this one first because you have to make it even because, and it's a lot easier to make a 3 an even number because I can just double it than trying to figure out how to make a 2 an odd number because we can't change the subscript. So that's not possible. And for our purposes, coefficients are whole numbers. So we make 1 more molecule of these. We do 1 fluorine with 3 chlorines. And now we have 1, 2, 3, 4, 5, 6 chlorines. We have 2 over here. We need 4 more to make 6. So we can do 1 more set, which gives me 4, and then 1 more set that gives me 6. Because remember, you have to fully represent the molecule each time. And we have 2 irons. And so therefore we have to make 2 irons over here. Now I have 2 irons, I have 2 irons, iron's happy. I have 6 chlorine, I have 6 chlorine, chlorine's happy. That means that this count of molecules becomes our coefficients. So you can go ahead and rewrite the equation down here using your color coding. So Fe, then instead of just Fe, I have to write a 2 in front of it because I have 2 molecules to represent. 2 Fe S plus, and then I have Cl2, so I can write Cl2, but I have 1, 2, 3 molecules to represent, so I write that 3 out front because remember your coefficient is how many of that entire molecule you need. Don't forget to write your states of matter and your arrows. And then I have FeCl3, I have 2 of them, so I write the 2 up front, so it's 2 Fe Cl3. Please don't forget to go ahead and write your states of matter after. Your equations will not be fully correct without the states of matter. And so this is how we went from written to word, word to skeleton, showed our work for balancing, and then our balanced equation is down here on the bottom. Okay, let's do another sample problem of going from written to balanced. And remember, the first step is to go from written to word. And the very first step is to underline and read this written reaction and figure out what the words mean and how they will translate to a word problem, knowing that we leave our compounds and elements alone. So I start with solid potassium hydroxide. Remember, solid is a little s. And that solid goes with potassium hydroxide. It reacts with, remember, reacts with, it does not say that it's reacting to produce, it reacts with, this is your plus sign. Liquid phosphoric acid. This liquid goes with this phosphoric acid. It's a lowercase l. That's saying the state of phosphoric acid. Now, phosphoric acid is in and of itself a compound or an element, so I leave it alone. It says, to create, there's your arrow, solid, that solid is a lowercase s, and that solid goes with your potassium phosphate. If I could, I'd draw an arrow down, but it would get a little messy. And is a plus, liquid goes with water, and that's a lowercase l. So now that I've kind of read and deconstructed what all those words mean, I'm ready to go ahead and write my word equation. So I have potassium hydroxide. And that is a solid. I have reacts with, which is a positive, a plus, which is also a positive thing. Phosphoric acid. Which is a liquid because that's what came before it. to create solid. This is where we put our arrow. If you are like me and you kind of run out of room, you can kind of put the arrow on the next line. Because I have larger handwriting. If you have smaller handwriting, good for you. It says solid potassium phosphate. So now we have potassium phosphate. And we go ahead and put the S next to it. Your and is a positive, and then we have liquid water. Our water is written, and then our state of matter is written after it. And that's how we've gone from word to written. Okay, so let's go from our word to our skeleton. Now, this is when I start talking about underlining and color coding, but this is also where I'm going to completely point out to you that we can physically see the word hydroxide, and we know hydroxide is a polyatomic, and we don't see it over here. So we know that hydroxide has to be split into its H's and O's independent of each other. We also can see the word phosphoric acid, and we see the word phosphate. This is when we can realize that phosphoric acid, based on our oxyacid naming rules, has a phosphate in it. And so I can go ahead and look and see that phosphates on both sides. I can treat phosphate as one element. So I'm going to start outlining this. Remember, our skeleton equation has balanced compounds. So we are going to be balancing our compounds with subscripts, but it is not a balanced equation, so we will not be putting coefficients. So we're going to say potassium's is purple color. And so that's going to be potassium, and then I'm going to write a K. And then I have hydroxide, which is hydrogen, which I'm going to make this red color. And then I have oxygen, which I'm going to make this kind of orange color, so this glittery orange. So it's going to be KOH. And don't forget, you still have to do your symbols in your color. So I'm going to do S. Then we have phosphoric acid, which is hydrogen. So you got to pull that orange color out for hydrogen over here. It's going to be H3. And then phosphate, let's make this kind of pretty pink color. That's going to be HPO4. And then again, don't forget, you still have to make sure you're color coding with your states of matter. So that's L and then arrow. Over here, I have potassium phosphate. We can go ahead and pull over our color coding for both potassium and phosphate. So I have K, that's not the right color, sorry guys. K3, PO4, and then we have to label that as our solid because it's a state of matter. And then our plus, because we have to add it to water, and water is our H2O, and that is also a liquid. And that's how we go from written to word, word to skeleton. And if you see what I've done, I may have switched up the color coding where I switched my hydrogen here. That's fine, an easy fix is just to take the color where you switch it up and just go over it, the one place where you messed up. Sorry guys, I really like that glittery color, obviously. Okay, so now we're gonna balance, and remember, especially over here with KOH, we have to make sure we're presenting both oxygen and hydrogen. So I have 1 K, that's 1 potassium, and you gotta draw one of these to begin with because you have to represent what you have. So we have 1K, 1O, and 1H here. Here we have 3 H's, and I'm going to fix the color coding down here so we can follow it. And we have 1 phosphate, because for every 1 phosphate, this comes with 3 hydrogens. Over here, we have 1 phosphate for every 3 potassiums. And over here, you have 1 oxygen for every 2 hydrogens. And remember, you can't just create part of a compound, you got to create the whole thing. And over here, because we have hydrogen both on here and here, you got to take the hydrogens over as a whole. So we have 1, 2, 3, 4 hydrogens to balance. We have 2 hydrogens over here. Hydrogen is not happy. We have 1 oxygen and 1 oxygen. Oxygen's happy. We have 1 phosphate, 1 phosphate. Phosphate's happy. We have 3 potassiums and 1 potassium. Potassium isn't happy. So both of our hydrogens and our potassiums aren't happy. Now, you could start balancing with the hydrogens, and that would be nothing wrong with it. But because hydrogens are in multiple places over here, and potassium's just in one place each, I'm going to recommend starting with potassium so you don't have to go back and do a lot of extra work. So we have 3 potassium over here. We have 1 potassium over here. We need 2 more potassium to balance it out. So I'm going to represent the full amount of potassium that I need. I need 1, 2, 3 full potassiums, and I have 1, 2, 3 over here. My potassiums aren't equal. But remember, you have to represent the whole molecule. So each one of these potassiums comes with 1 hydrogen and 1 oxygen. So now over here, I have 3 oxygens and 1, 2, 3, 4, 5, 6 hydrogens. Over here, I have 1 oxygen and 2 hydrogens. I need to represent at least 2 more oxygens, and I'm going to do that by creating 2 more oxygens. Okay, but remember, each oxygen comes with a side of 2 hydrogens. Can't create, just give me oxygen. And now if I look, by doing that balance, I have 3 oxygens, 6 hydrogens, 6 hydrogens. I am balanced. Remember, that is why sometimes you balance the ones that are one-on-one first, because if you were trying to balance hydrogens going back and forth between 2 compounds can be a little trickier. That's not to say that you can't do that, but this is a easier approach, at least for simple types of balancing problems. Now that we've balanced it, we can write our final equation with our coefficients. Now I have 1, 2, 3 for KOH because potassium hydroxide, because I represented 3 molecules. So that 3 is my coefficient. So I need 3 of the entire KOH molecule. And don't forget to write down your states of matter and your equation details in your other color. Now, for phosphoric acid, we have 1 molecule. So our coefficient would be 1, but you don't really have to write 1 as the coefficient because we've already written it one time by writing H3PO4. So that is fine. If we only have 1 of a molecule, you don't have to write the coefficient of 1. So that means for K3PO4, we only have to write it 1 time with no coefficient. This is only 1 of them. And again, don't forget to write your states of matter, your pluses and your arrows, because if those aren't done, it isn't a complete equation. For water, we have 1, 2, 3 molecules to represent, so that becomes our coefficient of 3. So we have 3H2O That's a liquid. And yes, I keep the color coding going so I can really see what's happening. You can go ahead and maybe write these all in one color if that would make sense to you. But that is how we go from written to word, word to skeleton, skeleton to balanced for this equation. Okay, let's do another example for going from written to word, word to skeleton, skeleton to balanced. Solid tin 4 oxide and hydrogen gas produce solid tin and liquid water. Now, remember your first step is to go ahead and remember that going from written to word, everything that is a compound stays in words, but all of your states of matter and everything else goes into equation format. So we're going to go ahead, I'm going to keep doing it in orange to underline what needs to be put into equation format. So solid needs to be put into equation format. So that's a lowercase s in parentheses. And that goes with tin 4 oxide and is our plus hydrogen gas. That gas goes with hydrogen, and that is a lowercase g in parentheses. Produce, the word produce is an arrow. Solid tin, that tin solid goes with tin, and that's a lowercase s, and is a plus. Liquid water, that liquid is an L. Now that you've done that, you can go ahead and write down your word equation. So tin 4 oxide and you go ahead and you put the solid after it. You're really not supposed to put it in like a space between them. And is a plus. Then you have hydrogen gas. Produces an arrow. Solid tin, so that's tin. Solid, and is a plus. Liquid water, so that's water. And then an L after it. And that's how you go from word to written. Okay, now we're going to go from word to skeleton. And this is when I underline all the different colors I'm going to use, because this is when you have to start color coding. And remember, skeleton is where you balance compounds. So you will be balancing each compound individually, whereas your balance is where you balance your equations and use coefficients. There's no coefficients, only subscripts in your skeleton. So I have tin 4 oxide. That's an ionic compound. You should be using your LCM method or your crisscross method in order to balance it. So for tin, I'm going to use this pretty purple color. For oxide, I'm going to use this, or oxygen, I'm going to use this kind of red color. And water is part oxygen, so I'm going to kind of underline it there. So for tin 4 oxide, I end up with SnO2 don't forget your states of matter, plus hydrogen gas. I'm going to use this kind of pretty pink color for hydrogen. Remember, hydrogen gas is a diatomic, so I write it as H2 and then G. Then I'm going to arrow over. Then I have tin solid. Tin's as a solid is just an element, so I can just write Sn. Then I can go ahead and write my state of matter after it. Plus, now I have water, which is H2O. And that is a liquid. Now that I have all of my equations balanced, And remember, tin 4 oxide, that 4 is not the amount of tin, that's the charge of tin. So when you're crisscrossing or doing your LCM, remember, you got to do it in the lowest common ratio. So instead of 2 tins and 4 oxygens, we have 1 tin and 2 oxygens. Okay, now it's time to go from our skeleton to our balanced equation. I'm going to keep using the color-coded method. I think that is the most visual and easiest way to solve it, but if you want to use any other method, that's okay, is because you'll always get the same answer. So remember, for color coding, you always have to draw at least one of every compound to represent what you have. So I have 1 tin over here for every 2 oxygen. Over here, I have 2 hydrogen. Over here, I have 1 tin. And that 2 hydrogen is diatomic. That's why they're touching. You're representing one molecule, which is H2. And over here, I have H2. And then I have 1 oxygen. You're representing molecules. So I have 1 oxygen over here. I have 2 oxygen over here. Oxygen isn't happy. Otherwise, I have 1 tin, 2 hydrogens, 2 hydrogens. So I really have to correct my oxygen count. So I have to add 1 more oxygen. So I'm going to draw 1 more oxygen over here, and each one of these oxygen comes with 2 hydrogen. Sorry about that, guys. 2 hydrogen. Now that I have balanced my oxygen, my hydrogen is 1 off. I have 2 over here. I need 4, so I need to make another molecule so I can get 2 more. Because this comes in pairs of 2. So I have 2, 4 hydrogen, 2, 4 hydrogen. I have 2 oxygen, 2 oxygen, 1 tin, 1 tin. I'm balanced. So now I can go ahead and write my balanced equation underneath, which is 1. I need 1 tin 4 oxide. So because I already have 1 molecule, I only have to write it 1 time, because you never write 1 as a coefficient. Don't forget to write your states of matter and your pluses. I have 2 of the hydrogen molecules, so I need to write 2 as a coefficient. Don't forget to put your states of matter. You have 1 tin, so you only have to write it 1 time. That represents the 1 molecule you have. You don't have to write it as a coefficient. And then over here, I have 2 of the water molecules. You write that 2 as a coefficient because you have 2 whole of those molecules. The coefficients tell you how many of each you have, not of the element, of the whole compound. So you have 2 H2 and then O's. And don't forget to go ahead and write your states of matter. And this is the balanced compound. You have 1 tin 4 oxide, 2 hydrogen gases, 1 tin, and 2 waters in order to balance this word equation. And again, that's how we've gone from written to word, word to skeleton, skeleton to balanced. And thank you very much.